All right, let's say you have the wave equation utt equals to c squared uxx, and the two ends are tied, so uat is 0, ubt is 0, so it's like the interval a to b. Imagine that there's a string tied to both ends, and you pull it, and then you release it, and then it'll vibrate, right? So the vibration is governed by this wave equation, and then in the initial condition, you have ux0 equals to some function of x, and then ut of x0 is some function of x as well. And this is the initial configuration of the string, and then this is also the initial velocity of the string. And since it's a second order differential equation with respect to t, you need to provide two initial conditions. So we've solved this using the separation of variables method. So we know that we can find the solution in this case, right? We even know the general form of the solution. The form of the solution we got was like uxt equals to summation of so it was something like a and cosine something t, right? Forgot. Well, this depends on this length and all that. C, maybe c t, c pi over n something, and then b and sine c n pi over lt. And then you also had some constant of sine of n pi over lx. So that was the general solution, right? So we know that an an and bn has to be obtained by taking the Fourier sine series or cosine series of these functions. That's how we got it. Yeah, but we haven't proven that the solution is unique, because we need uniqueness to be absolutely sure that this is the only solution. If we don't know uniqueness, then we might have to hunt for other solutions. Okay. All right. So how do you show that the solution here is unique? So let's say, suppose u1, u2 satisfy the left. Let's say you have this system, the PDE with the boundary condition and initial condition. Let's say you have u1 and u2. What should we do? How do we show that something's unique?
u1 equals to u2.
You have to show that u1 is equal to u2 by doing what?
Subtract them.
Subtract, yeah. So you say W is U1 minus U2, right? And you plug W in on the left side, and that gives you U1 TT minus U2 TT, which is same as U1 XX times C squared minus U2 XX times C squared. So that's same as C squared times W. So you can see that this W is going to satisfy this one and this one. I should have said equal to 0. This one. And then, how about these? So we'll have WAT equals to 0, WBT equals to 0, and then W of X0 would be 0, and WT of X0 would be 0. Okay. So what we want to prove is that if this is true, then there's no other choice but W to be 0. Okay? All right. So the way we solve this is by using the energy. We define energy to be integral of A to B of W T squared plus CWX squared dx. We do this. Okay. Now you might wonder where this energy came from. Well, this is very similar to our discussion about the highest point of the wave corresponding to the highest point wave squared corresponding to the wave. So it takes a bit of patience and calculation, but if you actually took this as your W and you plug it into this left side and you did a long calculation, you'll see that at the end of the day you get AN squared plus BN squared. And those are, AN squared plus BN squared would actually be the square of the amplitude of this sinusoidal wave for each of these. So it's the sum of all the energies. Okay? So that's how you can understand this. Another better way of understanding this is like there's a theory of Lagrangians and Hamiltonians where you can have the energy of the system defined and you write down the Hamilton equation and then you end up with the governing equation for the movement, and that if you start with this you can derive that equation. So if you can, there's a high-level physics argument where if you're given this energy and you're trying to find the mechanical system that would satisfy this, you get that as your equation. So that's something that I mean I haven't thought about it myself. I just know that it does exist. But it's also just too much to explain here. But let's just say that's the energy. Now, let's start with E of 0. What's E of 0? Well, E of 0 would be WT with, oh, by the way, E is a function of what? T. Is it a function of x? No, because you've integrated away x. So it's not a function of x. It's only a function of t. So when I say E of 0, I mean you're plugging a 0 into t. So what do you have? WT, you have x. W has function, W is a function of x and t, but you're plugging in 0 into t, right? You have square plus CWX x0. Okay, what's this value? WTX0, what is it?
GX.
No. W is not this one,
Oh.
it's that one. 0,
Oh.
it's 0. Here. 0.
Yeah.
And although we don't have WXX of 0, we know that W of x of 0 is 0, and you know, this is a partial derivative with respect to x, and you're fixing t anyways, right? So if you know that Wx0 is 0, then at least in the derivative in the x direction is still 0. We don't know what's going to happen for Wt of x0. Well, it says 0 here, but if that wasn't given to us, this is not going to allow us to say that Wt of x0, because that's like orthogonal to this direction that we have. But at least if we know this, then Wx of x0 will be 0. Okay? So we know that this is 0, that's 0, therefore E of 0 is 0 squared plus 0 squared, so it's 0. So we know that for this one, the energy of the system is 0, which kind of makes sense, right?
Can you explain why Wx is 0?
Right, so we're doing Wx x of 0, well that's defined as this, right? Now, let's write down the limit definition for that. What is that? That's limit of h going to 0 of w. You're fixing t, right? You don't mess with t, you only mess with x. So So let's just put t for now. That's what partial derivative is, right? You don't mess with t, you only put x plus h in the x direction, right? So we know this, but what happens when you plug in 0 for t? See, you're not taking limit t to anything, so this t will be replaced by 0. So if you know that this is true, this is just the definition of what partial derivative means. So if you plug in 0, what is w anything comma 0? 0, right? So this is 0, that's 0, so 0 over h, so it's going to be 0. Right. Yeah, but what I was trying to say is that this, knowing this is not going to allow you to say wt is 0. If you have wt, then that's totally different, right? Then this time you add h on the t side. So in this case, if you plug in 0, I know that this is 0, but I don't know what wxh is. So knowing this doesn't tell you that wt of x0 is 0. It's likely not, but in our case it is. But I at least know that wxx0 is 0. Okay? So that's equal to 0. Now,
isn't that equal to a constant?
Which one?
E0.
Oh no, it's a definite integral. If it's an indefinite integral, it's a constant, but it's a definite integral. So this will be 0 integrates to some constant, and you evaluate from a to b, right? If you plug in b into a constant function, it's c. If you plug in a into a constant function, it's c, so it's 0. I mean, come on, what's a definite integral? It's the area under the curve, right? But the area under the curve will be 0 if you have a 0 function. So that's what we have.
I think we don't need to use limits, just the derivative of 0 is 0, right? We know the w.
Let's get beyond that, okay?
Okay.
Yeah, all right. So E of 0 is 0. So now what I want to show is the following. Now I want to show that this is conserved all throughout the system. After all, that's what energy is, right? You have the conservation of energy, right? So I want to show that this is conserved, and if this is conserved, then that means initially it has 0 energy, and it's going to be 0 energy throughout, right? And when can that happen? When this is 0 and that's 0. So for all time t, this will be 0 and that should be 0, and that the only way that could be 0 is when w is 0. So that's how I'm going to finish the proof, and I can differentiate both sides by t. So here we're differentiating by t, okay? Maybe I should differentiate it by t. Then what will this be? What do you get if you differentiate this by t? Chain rule. 2wt times wtt. Yeah, you're differentiating twice in t. Right? Okay, how about this one? 2 wx cwxt, right? dx. Or you know what? C is just c squared, so bring it outside so that it's less convenient. Let me just rewrite it. C squared wx, wx times wx.
And 2.
2. Okay. Now what we do is we are going to take So I'm going to integrate this with respect to x. So I'm going to do partial integration by parts. Okay, I'm going to do integration by parts. And first of all, I'm going to rewrite WTT as WTT, I forgot to say it here, but WTT would be c squared WXX, right? So I'm going to rewrite this as 2 integral a to b of WT c squared WXX dx. And then for this second case, pull the 2c squared outside. I'm going to do integration by parts. What's integration by parts? If you have a product of functions, you only integrate one of them, right? So you only integrate one of them. But then minus, in the next stage, the one that you did not do anything to, which is Wx, you differentiate. But because this is an integral with respect to dx, by differentiating, I mean it has to be differentiation by x, right? So it'll be Wxx, Wt, right? And then dx from a to b. Okay, well, I'll have to erase up here and then continue here. Alright, so here I have 2c squared integral from a to b of Wt times Wxx dx. And then here I have plus 2c squared Wx, and then a and b are plugged into x, right? So it'll be Wx at Wt at minus Wx bt Wt bt. Okay, so that's what you get from here, right? Okay, and then minus 2c squared times this other one, so 2c squared. And let's switch these two around, so it's Wt Wxx dx from a to b. Now look, these two cancel away, right? And then now with the same argument here, see, this is true for all t, right? So if that's true, which one's 0? Is it Wxat or Wtat? Which one is 0? If this is 0, Wt of at is 0, or Wx of t? Still don't get it. See, this is a function that's defined for different values of t, right? So it only makes sense to differentiate by t. So if this is true, then Wt of at is 0. Okay? With the same reasoning that I had before. Okay? Yeah. And same thing. If this is 0, then Wt of bt is 0. So this is going to be 0, and that's going to be 0. So these canceled away. That's 0, so it's 0. Okay? So what does that mean? Well, that means both of these are 0. So our conclusion is that Wt has to be 0. Because E of 0 is 0, and then we just showed that E prime of t is 0. So that means we just solved that E of t is 0 for all t. So that means this value is 0 for all t. That means Wt is 0 and Wx is 0. But what's a function whose t derivative and x derivative are both zeros?
0.
Constants.
A constant.
Yeah. But again, if you have a constant and you apply these boundary conditions, then you have no other choice but to say that that constant has to be 0. Okay? So you've shown that W is 0, and therefore uniqueness is proved.